Hi, here we are discussing about a project low complexity implementations of real-time reconfigurable low-pass equalizer. Here, the reconfigurable digital filters are widely used in modern signal processing systems because it allows of filter characteristics such as a bandwidth and response to be changed in real time without redesigning the entire filter. Here, a reconfigurable low-pass equalizer is one such structure that combines a low-pass filtering and equalizations using a smaller number of control parameters. While this approach is flexible, but the existing hardware implementations often rely on general multiplier and frequent coefficients updates, which increases the hardware complexity, power consumptions and delay. It's making them unsuitable for real-time processing of time varying signals such as chip signals. These chip signals have a continuously changing frequency and therefore require filtering architectures that can adapt efficiently while maintaining a low computational cost. In this work, a low complexity reconfigurable low pass equalizer architecture is proposed to filter chip modulation signals in real time using a parameter control filter structures. The core method of this work is based on variable bandwidth filter followed by variable equalizer, where the most filter coefficients are fixed and implemented using a shift and add architectures instead of general multipliers, thereby eliminating online redesign and complex coefficients loading. Here, the chip signals are applied as a primary input and filtered to demonstrate the adaptability and effectiveness of the proposed architectures, and this waveforms is emphasized due to its growing importance in next generation communication system. Okay, so the novelty of this proposed work lies in optimized arithmetic reformulated and that reduces the number of adders, flip-flop and leading to lower power consumptions and reduced complexity and improved the timing performance. The complete designs is described in Verilog HDL and functionality verified using modulism and synthesized and performance comparisons are carried out using Xilinx RTX 7 FPGA platforms. Now we can verify the paper. So this paper is fully designed for a reconfigurable low pass equalizer filter. Okay, so here the RLPE architectures it will be used. Okay, so which means a real-time reconfigurable low pass equalizer. It will be designed with variable bandwidth VBW filters and followed by variable equalizer. Okay, so this two architectures is a major core of this architecture. Okay, so it will be support with this FR filter. Okay, with support of the FR filters, this architectures it will be designed, but compared to the existing architectures, it's have more number of multiplication for coefficients. But this paper they reduced everything and they will be introduced a SOI method and SHA method. Okay, so which means a shift and adder method architectures they will be used. Okay, so here they have designed 4 number of architecture design. Okay, so one is for VBW filter with a SHA and VBW filter with the SOP architectures and proposed RLPE architectures and VE-SOP architectures. Okay, here this is a figure 1 architecture, so it will be showing the proposed RLPE architectures. So this XN is an input. Okay, so it will be passing the signal to low pass variable bandwidth filters and followed by variable equalizer, and finally we will get a YN output. Okay, so here this low pass variable bandwidth filters, it's having a selection point with a different bandwidth and different channel. Okay, so in the existing method of the FR filters, it will be using for fixed coefficients method. Okay, but here it will be splitted with different bandwidth and different channel. Okay, the different bandwidth means, so example one particular bandwidth it will become with 0 to 50 megahertz means, so here the different channel means it will be passing with 0 to 5 megahertz and 5 to 10 megahertz and 10 to 15 megahertz, 15 to 20 megahertz. So okay, we can vary with the different channel using the one bandwidth allocations. Okay, so the same part we can utilize this architectures with a different bandwidth based architectures. Okay, so further this design we proposed with the 6G communication method of the chip modulation signals that will be used here. Okay, so here I'll show the reference paper. Here this is one of the reference paper, chip spectrum signaling for future air ground communications, frequency shift chip modulation for LoRa modulations, and the chip signals it will be used for the PSK, okay, for demodulating based on F or FFT, okay. And the basic concept of this chip signals it will be used with this method, okay. So here this one, so linear chip waveform, sinusoidal wave that increases the frequency linearity over time period, okay. So this same method we have used here, okay. So before this chip modulations, we need to verify this concept, so the filter architectures, okay. So the figure 1 it will be showing the basic architecture, and the first architectures it will be come with this one, the figure 5, implementations of VBW filters, and subfilters are supported with the FR direct form, okay. So here this is the SOP architectures, okay, which means the sum of product architectures, okay. And this one is a X of n filters, okay. So these are the D flip-flops, and these are the adders, and this is the SOP architectures. And finally the B2 B0 it will be coefficients, it will be multiplied with here, okay, and after that we get the final output, okay. So this is a VBW output, okay. So once it will be completed, we need to give the VE architecture. So this one, it's a VE architectures. So using this VE architectures, we filter out it again, okay, with the support of different channel form, okay. After that we taken the final output, okay. So the next architecture is the SHA architectures, it will be showing in figure 6, okay. And the next architecture is SOP form, okay. So this one, okay. So here these are the architectures that will be handled in this paper. So this architectures one by one we developed in Verilog HDL, okay. So the initial architectures of the RLPE we have tested with the 3 number of signal form: ECG signal, sine wave signal, and RLPE chip generations, that is a separate one, okay. So initially we can show the ECG signal form, okay. So here this one, okay. So here you can analyze the data input, data output, and filter output, okay. And if we can change this ECG signal to sine wave signal, and easily we can plot the sine wave filter with support of this RLPE, okay. So this is a sine wave pattern, okay. So here this is a data input, this is a VBW filter, and this is a VE filter output, okay. So the next thing is the proposed method RLPE. So this one is a RLPE method, and this one is a RLPE with chip modulations, okay. So here we have developed the VB filter, okay, with the SHA architectures with chip modulation, SOP architecture with chip modulations, and realization design, and VE architectures with the chip modulations, and proposed RLPE with chip generation, okay. So here we show this proposed RLPE architectures, okay. So this is the proposed RLPE architectures, okay. So this is a Verilog HDL code, and so this one is a initial signal. So this is a sine wave form, and the next one is a chip signal modulation, okay. So here you can analyze this, the filter output and filter input, and the VBW output, VE output, okay. Further this work we have synthesized in Xilinx Vertex by FPGA, okay. So here this is a synthesis report for RLPE architectures, okay. So this one is a proposed with the chip generation, okay. So here for chip generations we can't do with the same base paper architectures, okay. So it's a complicated one. We have remodified the architectures here, okay. So why? Because the sampling part it will be come with the complications in the chip modulations, okay. So why? Because the X of n it will be sampled here, and the feedback of the X of n again it will be added, okay. So it will be not possible in chip modulation, so we remodified the architectures. After that we have created this chip modulation signals, okay. So this one, so here the chip modulations, here it will become with a frequency low, and time period increases, okay. So it will become with a more number of frequencies, okay. So example, so here you can measure it's come with a 900 kilohertz, okay. So here you can measure it will become with 4.23 megahertz frequency, Okay, so if the time period increases, okay, so it will be come with more increases frequencies. Okay, so here you can verify it. So it will become with a 15.38 megahertz. Okay, so yeah, 13.33 megahertz. Okay, so for accurate level means we can use this sine wave and we can plot it the frequency in accurate. Okay, so 12.19 megahertz frequencies will be plotted here. Okay, so data input. Okay, so this is a complete setup, and so this part. Okay, so this one is a chip modulations. Okay, so that's why the logic size it will be reduced here. Slice registers, LUTs. Okay, so normal operations means it will be come with some more logic size. Okay, so here I'll show that. Okay, so here it will be come with the 106 in proposed RLPE method, and here it will be take only 98 and 398 LUT. Okay, so here you can analyze the schematic for RLPE and variable design. Okay, so array multiplier and SHA network architecture. Okay, and the next method is a SOP architecture. Okay, so here you can analyze it VBW filter SOP architecture. So this is one. Okay, and next one is a CMM architectures. Okay, so this is a one. Okay, so SHA with the CMM. Okay, which means a SHA architecture. Okay, shift and add architecture method. Okay, so here you can analyze it. So this is a core. Okay, so ripple carrier method and the delay method. Okay, and so this work we have compared it here. This is a comparisons table. Here you can analyze the existing comparisons and propose comparisons. Okay, and we have written abstract document for this project. Okay, so title, base paper abstract, improvement of the project, proposed title, proposed abstract, general notes, and existing systems, disadvantages, proposed systems, advantages, and related notes for the softwares and literature survey, and finally come up with references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXFE, you not only get expert-guided projects starting from RIS 6000 transparency, but also enjoy unmatched benefits like RIS 1000 to off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXFE for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXFE guide you through your research journey with flexibility and expert support. Thank you.